Alright, what's going on? I am Professor Caudill. Today we are on relative motion. So, reference frames, that's like your perspective. Position, velocity, vector equations for that relative motion. Draw the position, velocity, as one dimension, two dimension. Okay, so motion, train going 10 meters per second. So I'm guessing relative velocity is the velocity of the other minus velocity of the person. Let's just say train 2 minus velocity of train 1. Thinking that's how they're thinking of it. Meters per second west. Okay, so it should be V naught minus V, where V is the final velocity. So that will get you -5. You move the negative sign into the I hat. Then it's 5 meters per second in the west direction. We introduce relative motion tension. Okay, fair enough. Velocity of the train on Earth, I think, is what the T means. Train in Earth. Okay. Say the person gets up. Okay, so this reminds me of how you define a matrix. How you define matrix multiplication. So it's saying just as this is true, it's also true when you have two matrix. Okay, so this is a n by m matrix, and this is a n by m n by n matrix. It's probably hard to see with the squares, but to do matrix multiplication, I mean, in this scenario, n equals m, but if the dimensions were not right, you would do it like this. So this first number is the rows. So if the column of this, the amount of columns here, if 2 does not equal the amount of rows, then you can't do matrix multiplication. So I just feel like they're going to, it just makes sense that there'd be a way to describe this as a matrix. I don't know if they will do that in this book, but what is the field for matrix? I'll verify. Dimensions, yeah. So columns of A must equal the number of rows of B. So if it's n by m, then we'll have shape. So C will be n by n. So what is this saying? The columns in A, so the columns is m, 2 columns, must equal the rows of B. So 2 rows. M equals m. Okay, so it's important to draw analogies when you can, because some people like Douglas Hofstadter, they argue analogy making is at the heart of intelligence. I'm reading their book, Fluid Analogies, something, FARG by Hofstadter is a book I'm reading right now. It's about sequences. Okay, so adding the vectors. So going 10, the person is walking with respect to Earth. 8, with respect to the train. Okay, so the subscripts matter just like the dimensions of the matrix matter. Okay, I guess we could just ask, is relative motion in physics ever described Okay, so I guess we won't really see that till specifically velocity. Okay, it's really sticking to Lorentz transformation. Isn't Lorentz transformation involved in integral? Pretty sure there's an integral. No, no, it doesn't. So yeah, I think we're going a little too outside the box, but all right. So play with concepts to describe motion in 2 dimensions. So particle. Okay, so R of a particle in S and R particle in S prime reference frames. This is the R is the position vector in multiple dimensions. Okay, so we now apply these concepts. Okay, I'm seeing what they're doing. It's kind of like um, it's kind of like a Mandelbrot function. Zooming in, uh, kaleidoscope being a Cartesian coordinate system. Okay, so R, the position function of the particle in S is position function of P S prime plus S prime S. So what is this saying in English? Position of the particle in S prime reference frame added to position of the S frame in S. And you can obviously see these match, which is important. And like the matrices, you can see PS is here. Notice how in the outside terms in matrix multiplication are the same n by n. It's likewise here, PS. So it should be easier to understand this with a linear algebra background. involving more than just vectors. Okay. Okay, so this is the exact same for velocity. Okay, so this is looks a little bit more complicated, but I can see the rules are the same. So PC, PC, AA, BB. So if you know, Lorentz transformations are a linear, like you're taking something, multiplying it by a matrix. That's a linear transformation. So that involves matrix multiplication. So I'm thinking in a more advanced physics course, this subject of talking about reference frames, it's like a linear transformation. You're taking a set of coordinates. So what's a linear transformation? I don't have the best understand. Like, I'm not an expert, but for what I suspect, it's like taking one set of it's like taking a function of one set of coordinate systems and turning that into another set. So if this is our initial reference frame and we want to express that in a different reference frame, we do a linear transformation. So if this reference frame is, say, 1, 2, 3, 4. No, let's just say it's a vector, velocity vector. So then let's say it's R. Then f of R would be some matrix M times R. Okay, so this matrix, if this vector is 3 by 1, then this matrix must be 1 by 3. So therefore, this would be 1 by 1. Well, not necessarily. This would just be n by 3. So this output would be n by 1. We can multiply because the dimensions are the same. So this would be 3 rows. So m would be 3 columns. A1, B2, A1, B1, C1, A2, B2, C2, AN, BN, CN. Okay, so I'm thinking to express a position vector. So that would be 0. So this would be 0, and this then the result should be another vector, right? In the same number of columns. So that should be vector 1. So you can see how reference frames are really just a linear transformation, and I've arrived to this just through the analogy of matrix multiplication. It just makes sense. Seeing vectors, seeing position function, expressing position functions as vectors, and if you're trying to move a vector from one coordinate system to another, or one origin to another, you're just doing a linear transformation. And also the order here matters. Linear transformations are always, matrix is always on the left. So when you see something like AX equals B, okay, this is how you solve like systems of equations. I don't want to get into it right now. I'm not gonna like break these down. Like you can basically say like, okay, A1 X plus A2 equals B1 A2 X2 plus A3 equals B2. So what they do is they convert this into a vector. They convert this into a vector. And then they convert this into a vector. So I don't know. This part might not be exactly correct, but and this might be a matrix. I wrote a vector, but the A is a matrix. So, but yeah, that's how you convert a set of linear equations into this form, and the matrix is always on the left side of the vector because algebraic rules. Okay, so it might seem like a long tangent, but I think it's, you know, valuable to make an analogy when it's reasonable. So, all right, so let's move on. Motion of a car relative to a truck. So we have a car, we have a truck, car, truck. Okay, he's traveling south. Okay. Car, so truck is traveling 70 kilometers south. This is a truck. Okay, and the car is traveling east. Okay, so the car is traveling car is traveling 80. Um, the, the units should be kilometers. Okay. Okay, so truck's going this way. We can say negative J to express negative J hat to express it's going south. This we can say I hat. Um, Velocity of the car relative to the truck. Okay, so let's make our reference frames. So we want the velocity of the car relative to the truck. So that's going to be something where it's going to be C. It's definitely going to be C. And then something T. So it's going to be the car relative to the car. The car relative to the car. I don't know if that makes sense. Okay, so let me just write my first guess. Okay, so not quite. They're doing Earth. Okay, so easy enough. So you can see how these match. Okay, so the velocity of the car respect to the Earth is 80. Okay, so how do we get that? 80. Okay, so we're in a global. When we're saying we're in Earth frame, it's really like a global frame. So yeah, so that'd be 80 plus negative 70. So 10 meters per second. And we need a direction. I'm pretty sure we need a direction because this book treats velocities as vectors. So I'm going to just guess I. All right. Never mind. They're making it harder than I thought. VTE is this. Okay. Oh man. Okay, so like this, there's no way I could have done this until they told me this rule. VET is negative TE. Yeah, so that's kind of bummer, but so really should be, is it just 80 then? So it should be positive 70. So okay, so I'm guessing 80 plus 70. Okay, so yeah, so we had to convert this to that. So we had VTE equals -70 J. So then VT is 70. So we just swap the sign. We can swap the subscripts. That's pretty cool. I wasn't expecting that. So they're treating. They're making a triangle out of this, which also wasn't expected. We've done that stuff like this all the time. So we solve velocity. Okay, so remember the book uses weird notation for the norm. I like the double bars personally. So it's going to be square root of V C E dot V okay. So that's not, is that right? I don't think that's right. It would be VCT dot itself. Um, so what we would be saying is VCT is 80, 70. So when you dot, it'd be A squared plus 70 squared. Okay. So CT is 80, 70. Okay. Makes sense. It's just like another way to look at it. Might be useful for you, might not. Obviously we can calculate this all day. I don't really see I don't see it necessary to do it ourselves, but okay, so two things that threw me off here. First, it's this equation that you can swap the subscripts by swapping the sign. And then next was the triangle. That definitely surprised me. Um, Obviously, what they're doing is they're moving. So they swapped this. So yeah, so they swapped it. So this is TE. So if you swap it, then it's VET. And then this would be here. Okay. So our final answer is VCT. So we're just moving. You kind of make the triangle until you first flipped this. So when you flip this, then you can say, okay, we can move the origins, these two origins, we can put them on top of each other. and then we can connect them. All right, let's try another one. All right, so we have a boat heading north in Stillwater. So let me make this bigger. It's going east 3 meters per second. This is going 4.5 meters per second. What is the velocity of the boat with respect to Earth? Okay, so this is the boat. This is a river. Okay, so first we have to describe this as the velocity of the boat. This is respect to the river, I think. This is velocity of the river with respect to the Earth. So we want the velocity of the boat with respect to the Earth. So we can take velocity of the boat with respect to the Earth, respect to the river. Okay. So I don't, as far as I can tell, I'm not seeing we need to do any subscript swapping. Dimensions match. So it should just be easy enough. The reason why I'm kind of skeptical is when they first define this here, why is it when they define it like this, why is it not a dot product Pythagoras theorem here? But they want us to do it over here. So this makes me kind of skeptical of what the book's doing. Is VBE 4.5 squared plus 3 squared, where, you know, we're putting the tail, putting the origin of this on the tail of this, and drawing a vector that connects them. So, or is it simply 4.5 plus 3? So this is where I need a second opinion. Okay, so the book's favoring the dot product. So I think the book's like, I think these definitions are kind of misleading. It really should be this vector is the, because this is a hypotenuse, basically. Basically what this is saying is this is a hypotenuse on the left side of the equation, and that these are the components of a right triangle. So really it should say this vector is the square root of the sum squares of those. Just like they did here. Notice how this problem they didn't add anything. They say it's this, but then they do this. I think I know what they mean though. I think these have, you have to think this has an I hat, J hat, K hat. So maybe they're just not doing the whole problem here, because when you get the magnitude of VCT equals 106, and you get the theta of VCT is 41.2 degrees northeast. Okay, so what do you do with these two numbers? You plug it in. So VCT is 106 cosine 41.2 degrees I plus 106 sine 41.2 degrees J. Okay, so then you're expressing this vector as some constant plus another constant. So basically you'd be specifying this and that, or it might be plus C K hat if you're in three dimensions. But that makes it hard, because if we're in 3 dimensions, I don't really know how to solve for the K hat part. And I think the book is skipping this intentionally, because that's probably pretty math intensive. So I think they answered that question partially, because answer it fully might be too much, at once. Okay, so flying a plane in a wind. Pilots fly this plane due north. Okay, 300 meters per second, still air. Velocity of the plane in still air. So let's say this is just your ideal air. So air with no subscripts or no apostrophes or primes. A wind is blowing out northeast at 90 kilometers. So I'm thinking it's saying a wind is coming here. Velocity of the wind negative 90 meters per second of the velocity of the wind with respect to the Earth. So is this Earth as well? Will be still air. So our final answer is the velocity of the plane relative to the Earth is going to be, okay, so the addition makes more sense if you're thinking of it in 3 dimensions with an I, J, K hat. So they only partially answer the question first. Okay, so it would be the velocity of the plane with respect to the air plus the velocity of the wind with respect to Earth. So these do not match these. Okay, so we need I know we're gonna have to swap this. So this should be the velocity of the Earth with respect to wind. So then we swap it 90. I think that's what we have to do. So let's just change this to the wind. So let's say this is W, this is a W. I'll rewrite it so it's clear. So these match, and these match. Okay. So the norm of this should be so I'm wondering if the angle, because it's coming at like a 45-degree angle, because it said northeast. So if it's coming at a 45-degree angle, I don't know if we might have to break that down into components. So I'm not sure if we can do this or not. If I just blindly follow the math, then it's that. Well, I think it's more difficult than that though. So they're doing PA plus AG. I don't know what their A is the ground. Okay. I put the earth. Same thing. 63 over 300. How did I get that wrong? Where is the 63 coming from? All right. Kind of I don't know. I just don't like this chap this section. I think it was kind of poorly explained. It seemed kind of rushed, I think. But it is what it is. So we got 9 minutes. We can review. So these are all the keywords. Centrifugal acceleration is pretty cool. So position equation, these functions times the unit vectors. Okay. I wish the book, it does all that and defines it as this. You could just write it as that. You could use Newton's notation, saying vector r, the dot of that. I know when you get like F equals MA, I'm pretty sure they do that. Force is MA. I think it's something like that, but I've definitely seen the dot product in physics, so it's kind of weird that this book doesn't. It's like, if you're gonna be conventional, then do everything conventionally. Don't pick and choose, you know? I feel like they're kind of picking and choosing with that regard. So, likewise, we could write velocity is so we could just write v is x I plus y I don't know if that's easier for you, or you can write it as r the derivative of r. These are all saying the same thing. Velocity is the derivative of the x function. And I've omitted like the t's. Like when I say dot this, there's a t here, but that's kind of implicit. V average. So displacement and average are kind of related. So it's like, again, you could just write V average as delta R. You could shorten these, and I wish the author would shorten them as much as you can. average velocity is the displacement divided by the difference in time. Same with the the A. That's your derivative of the velocity, I. So I don't know if this notation works here. Um, I don't want to like say the wrong thing here. So I'm kind of cautioned. I've added a subscript. I'll have to think about that more. See if that's right. Okay, so you can definitely do it like this though. Okay, and this is just saying it's the same thing as saying second derivative of y e j hat dot dot dot. Get the point. Um, so we got some new equations. Most of this is like kind of review. Yes or no. It's kind of like okay, but time of flight definitely that'll be one we need to remember. Maybe not remember, but when we do the homework problems, we'll probably be like on this page. It's kind of, I guess it does make it nice that everything's just in one place. So you can see how time of flight and range they're almost the same. V naught times they're almost the same, but not really. Um, so in a circular motion, so remember when you're differentiating, if you're doing d theta sine, let's say alpha theta, it's going to be you have to do it's going to be cosine alpha theta times the derivative of the inside, which is theta theta. So derivative of the variable is 1, so it's going to be alpha cosine alpha theta. If that makes sense. So basically what I'm saying here is when you're differentiating sine theta with a constant, you need to pull it out. And that's how you get the omega squared here. All right, so we're out of time. Um, a lot to put together here. Doesn't seem too overwhelming. It's just, you know, I can see like if you don't know much calculus, if this is like the first time you're seeing all of this, might be a lot, especially with the unit vectors. Um, I've gotten pretty used to them pretty fast, given my background. But yeah, this stuff gets a little tricky. This might be really ugly for some people. It's kind of ugly to me too, but these might be ugly, but these are not too bad, really. When you're comfortable with the calculus and everything, these aren't too bad. So yeah, we'll maybe we'll spend some time reviewing, and then we'll get to homework questions. We kind of blew through this chapter, but I think I took my time on it, so I think it might have just been a short chapter. So, all right, thanks for watching. We'll see ya.